Hello. This is a continuation of what was started on in class, which was the derivation of sum and difference identities. I decided to write out most of the derivation of the first identity to save time in the video. So a quick review of what we already did. This is a unit circle, and we chose a random arc. Actually, it wasn't, yeah, a random arc and a second arc, although I didn't draw them here. So the first arc was from here to here, the second arc was from here to here. So the difference between the two arcs is right here. And then the red line is a chord from the endpoints of the arc. And then we shifted that arc down to the x-axis so that the coordinates of one of the points would change to 1, 0, and then the other point would now become cosine of a minus b, since the long arc was arc A, and comma sine a minus b. And we drew a chord between those two endpoints, which should be the same distance as this chord. So then using these 4 points, or I should phrase it, 2 pairs of points for congruent arcs, we can express the distance of each of these chords in 2 different ways. So here's the distance formula for this chord, and here's the distance formula for this chord. And then the algebra is done here. This first step is from here to here is squaring both sides and multiplying out these binomials on both sides. And then using Pythagorean identities, I get a 1 plus another 1 on the left, and on the right this and this makes another 1. I already have a 1 here, which came from the squaring here, so I have another 1 plus 1. So those are going to go away. And then I have these 3 big terms left. So there we are. Each of these 3 big terms has a -2 as a factor, so I divide both sides by -2, and I have this. And then using symmetry, I just change sides, and I have my first identity. Cosine of a minus b is this, cosine a cosine b plus sine a sine b. So the next 3 identities are based on this one. So this is the main one. So I'll just call this number 1. Put number 2 over here because I need a little bit of room. So cosine of a plus b we can express as cosine of a minus negative b. So now since it's in the form of something minus something, I can just use the first identity. Cosine a times cosine of negative b plus sine a times sine negative b. And I can still do something else. Now, if you think about the unit circle, the cosine of an angle or an arc is going to give you the same value as the cosine of negative that same angle or arc. I can illustrate it up here. This angle and this angle. If this is theta and this is negative theta, they're going to give you the same cosine value. So I can express this as cosine b. Okay, now over here we have sine of negative b. I'll go back to the same drawing. So here's theta, here's negative theta. Those two are not going to have the same sine value, but the sine value of this one is going to be exactly the negative sine value of the one in quadrant 1. So that means I can express this as minus sine A sine B. And there's my second identity. Okay, so notice the difference between the first two. They have the same structure. You've got a product of two cosines and a product of two sines in each one. But the operation between those two terms is the opposite of this operation here. Okay? Okay, the third one is going to be the sine of A minus B. Okay, to do this one we need to remember something that we discussed before, and that is it is true that the sine of theta is the same as the cosine of 90 degrees minus theta, and also cosine of theta equals sine of 90 degrees minus theta. So I can express sine of A minus B as cosine of 90 minus A minus B. And then I can distribute this negative to get 90 minus A as my quote first angle plus B, because I'm distributing that negative. So B is now my second one. So now this is in the form of cosine of A plus B. Okay, so now using that identity, I can rewrite this as, I might need more room, so I'm going to go back here. Okay, there I use the second identity. And then I use the first identity to do this. Oh, and then I'm going to rewrite this. Since I haven't derived sine of A minus B yet, I'm going to rewrite this as cosine of A sine B. Okay, then I can simplify this part. Cosine of 90 is 0, so that's going to go away. And sine of 90 is 1. So 1 times sine A is sine A times cosine B and we'll switch the order around here. And so there's number 3. Okay, the structure of number 3 quite different than 1 and 2. Each of the products is the product of a sine factor and a cosine factor. Sine factor, cosine factor. And they're each, the sine one and the cosine one are of different arcs or different angles. Okay, and then the fourth one, I'm not going to go through that whole thing again, but the fourth one, you can use similar algebra and substitution as I just did to get number 3. To get sine of A, cosine B, plus cosine of A, sine of B. And those are the four main identities for sum and difference. Okay, so from there you can also derive the tangent ones. So the tangent ones, you just use the sine and the cosine identities, plug them in, and then you'll eventually get something that actually is not very simple looking, but you'll get used to it. So that's tan of A plus B, and then tan of A minus B, you can probably guess what it's going to be. So again, you start in a similar way. And eventually you get to this. Okay, so those are the sum and difference ones. Now here's a couple of examples. This group of identities is quite practical, actually. You don't just use it to prove other identities. For example, if I wanted the sine of a weird angle that is not normally memorized, like sine of 15 degrees, then one thing I can do is express the 15 degrees as a sum or difference of two other angles. So I can write it as sine of 45 minus 30, because I know the sine of 45 and I know the sine of 30. And then I know my identity too, so I can say this is the sine of 45 times the cosine of 30 minus sine of 30 times cosine of 45. Plug in all the values that I know. So rad 2 over 2, cosine of 30, rad 3 over 2 minus sine of 30, 1/2 times cosine of 45, rad 2 over 2. So that's rad 6 over 4, rad 2 over 4, or rad 6 minus rad 2 over 4. And there I have the exact value of sine of 15. I'll do one more example using the tan. So tan of 75 I can express as tan of 45 plus 30 and then use my identity. So that's tan of 45 plus tan of 30 over 1 minus the product of tan 45, tan 30. And then plug in all my values. Tan 45, that's 1, plus tan of 30, it's 1 over rad 3, over 1 minus, tan 45 is 1 again, 1 over rad 3 for tan 30 again. And then you can go ahead and rationalize that. You know how to do that. So there's the practical use, or one practical use of this batch of identities. And of course, use these identities to prove other identities. Okay, I'm going to go ahead and derive another batch of identities that involve more than one angle. And these are easier to derive. So these are double angle identities. The first one we'll do is sine of 2a. So sine of 2a I can express as sine of a plus a. And now I can use the identities I just derived to express this as sine of a cosine of a, where this a is the first a and this a is the second a, plus cosine of a, the first a, times sine of a, the second a. But these two terms are the same, so there we go, that's derived. And it's easy to memorize too. Now cosine of 2a starts out the same way. Now I use one of the identities from before. Cosine of a minus sine of a sine of a. And that's cosine squared of a minus sine of squared of a. Looks like one of the Pythagorean ones, but it's not. So that's the second one. And this second one can be expressed in a couple other ways that are convenient and practical, because I can replace either this or this with something from the Pythagorean group. So I can replace this with 1 minus sine squared and turn the whole thing into 1 minus 2 sine squared. Or I could replace this with 1 minus cosine squared and turn it into 2 cosine squared a minus 1. So all three of these are, as they're all about the same level of practicality or use. And then the third one is, of course, tan of 2a. And same as the other two. First start out like this, and then use the identity from before, the last group. Tan a plus tan a over 1 minus tan a tan a. And that becomes 2 tan a over 1 minus tan squared. Okay, and so there you are. Those are the multiple or identities involving more than one angle, and then a more specific group known as the double angles. And that's enough of derivation. I'll do a couple of examples for these double angle ones. Okay, so I'm given that there's an angle A whose cosine is -3/5 and is located in quadrant 2. And quadrant 2 is important because it could be in quadrant 3, and if it's in quadrant 3, then the sine is going to be different for the tangent, and the sine would be the sin sine would be different as well. So we know the angle is here, right? Cosine is adjacent over hypotenuse, so this is our situation. So I'm asked to find all three of these values: sine of 2a, cosine 2a, and tan of 2a. So first of all, sine of 2a, I know from the identity, is 2 sine of a cosine of a. So now that I have my triangle, this side is 4. Now that I have my triangle, I can just plug in these ratios. Sine of a is 4/5, and the cosine of a is -3/5. Simplify, -24 over 25. Cosine of 2a, that's going to be cosine squared of a minus sine squared of a. So the cosine of a is -3/5, as we know, and I'm going to square that. And then I'm going to also square the sine of a, which is 4/5. So that's 9/25 minus 16/25, or -7 over 25. And then finally tan of 2a, which is 2 tan of a over 1 minus tan squared. Okay, so we're in quadrant 2, remember? So the tangent is -4/3. So I'm going to write that here so I don't forget. -4/3. So 2 times -4/3 over 1 minus the square of this, 16 over 9. So that's -8/3 over -7/9. And that'll be positive 8/3 times 9/7, or 24 over 7. Okay, so this exercise is basically just making sure you know the identities, making sure you know where the triangle is located, so you have the right, so you know which trig ratios are positive or negative, and just plugging them in and simplifying very carefully. All right. Okay, so there you go. There are the double angles. Have fun with them.